And in the meantime, I'm going to define this amplification factor as capital A sub F, sub capital F, to be the product. Actually, AF is defined as a ratio, but delta maximum is defined as a product of the amplification factor and eccentricity. So I'm going to write this one to be AF times E. This is also delta maximum. By definition, this is what I want to define. Now, how do we figure out the expression of AF? And we can find out the expression of AF simply by this. Y maximum plus E equals to second K over 2 minus E times this plus E. And this has to be AF times E, right? So this, of course, as you know, that it will cancel out one of the E's. Therefore, this whole thing will simply just become second K over 2 times E. Correct? So what is the expression of AF? The expression of AF is just this. Yes, just second K over 2, which is this. Therefore, the expression of amplification factor, AF, in this problem equals to second KL over 2. So this is only for this problem. Now, why do we need this? It's because it so turns out that amplification factor is related to maximum moment. So once you have determined the amplification factor, expression of the amplification factor, maximum moment is simply amplification factor, AF, times P times E, which is the moment produced by eccentricity. So that's one reason why we want to find out what is the expression of amplification factor, because with that, you can just convert force into moment. Then you can find out what is the maximum moment. So from here, we can find the maximum expression of maximum moment. Like what we did before, we have the maximum deflection, right? Now we have the expression of maximum moment. What about maximum stress? This will be step 9, right? Is that right?
Yes.
Okay. So in step 9, let's find out what is maximum stress. Stress, as we know that we're going to use sigma. That means we are looking for sigma maximum, like this. And in the column cross section, the maximum stress usually equals to this. This is coming from strength of material equals to axial force divided by cross-sectional area when you have only axial force. But when you have the couple action of force and moment, there's a second term. That's the moment term. That equals to maximum moment times the distance from the outermost fiber to the neutral axis divided by mass moment of inertia, which is capital I. So this is the expression from strength of material. You must have seen this before, correct? You must have seen this before. Okay. All right, then, so we can just plug everything in. Then we can find out what is the maximum stress. So P is still P. P is just being P itself. Maximum moment is what? Is AF. And what is AF? AF is, in this case, because we have AF to be what? Second KL over 2, right? And the maximum moment is just AF times P times E. So I can write it this way. The whole thing is actually this. Here is P times E times second, right? KL over 2. Correct? And times C, like this. So what we did here was just to plug in everything we know for maximum moment into here, right? Now we also know that at buckling, that means P equals PCR. That also means what? That also means K over 2 equals pi over 2, right? That's the case when buckling occurs. But here, we didn't say that the P is going to be at the buckling, correct? We said P is just P. So this is the maximum stress for any values of P. We haven't said that P is PCR. We didn't say that. This is just a general expression for maximum stress. However, we can write this expression this way. You can take this one out. You can write it like this. You can write this to be P times E times second. Now I'm going to reverse things a little bit. I'm going to write this to be pi over 2 times the square root of P over PCR. So I'm going to write it like this. And the whole thing times C divided by I. So here the question is, how do I get this to become this? All right, how do I get from here to here? Why don't we take a break? For how long? Now it's 37. How about we come back at what? Well, 10 minutes. That means 48, right? How about we come back at 48? Think about this. Okay.
Professor, I have a question about when you started doing differential equations in the first example we went over today.
Mm-hmm. Yes. Which part?
So how do you get those base equations for YC and YP?
That's from differential equation. And of course, that I suppose that doesn't really answer your question, right?
I went to tutoring after we went over that first example a couple weeks ago, but it wasn't very helpful. He basically was just like, yeah, this is YC and that's YP and that's that.
Right. You, in order to really understand, okay, let me try this. suppose you have a second order differential equation, like in the form of this. Suppose it look like this. And if you just look at the left-hand side, that consists of a unity coefficient times the second order derivative of the primary variable, which is y here, plus a coefficient. And this coefficient in here is a k squared, but it can be anything, times y. And the general form usually can be written in two different formats. You can either write it in terms of an exponential function, or you can write it as the summation of a sine function and a cosine function. If we answer this question, let me try what is the best way to answer this. The reason why it could be either this or it could be another form, but that's the reason why the other form works is because of mathematical equivalence. Summation of sine and cosine equals to exponential function. So complementary solution can also be written as this. You can also write this equals to, I don't want to use the same coefficient, so what about I use d times exponential function of k times x? You can also write this, and plus c. This is the general form. You can also write it this way. And then all you have to do is to determine this coefficient d and this coefficient d. Why it has this form is because with the minimum number of coefficients you can evaluate or satisfy the conditions provided in the differential equation. So one way to explain this is because you have a differential equation here, and this differential equation in theory contains a lot of different kind of solutions that will satisfy this differential equation. So the differential equation is merely a condition that lots of different solutions can satisfy this one, right? Now what we found is that if you use either an exponential function or is a sine or some combination of sine and cosine functions, it will satisfy the condition described by this differential equation. So that's a mathematical way to say it. And I don't want to say it's a mathematical coincidence, but rather it's more like a mathematical consequence. So let's come back to here. Okay, so how do we get this? How do we know k over 2 can be written as pi over 2 over p over ei? And you can actually try to derive it from what? From plugging in the expression of PCR into the expression into this here. So I'm going to leave it as some practice because we have other things we need to talk about. How do you figure out that this one can be backed? If you like to figure out, just plug in this. PCR is pi squared ei over L squared, right? Just plug it in. Plug in this one. And by canceling out some of the terms, eventually we'll go back to k over 2. So this is the first one you need. And the second one you need is what? Is remember that P and K, they are always related. And PCR, also keep in mind that PCR is not P. PCR is not P. When PCR, critical load, equals P, that corresponds to only one instant, which is at buckling. So recall this. This is also an important concept. This is what we began with, right? We said that we have a loading here and you have deflection, whether it's a positive or negative, doesn't matter. When you start loading whatever the structure, in this case, a column, the force will start from 0.